I'm going to cover kinematics and the conditions of motion. As viewed by a Physics 12 student. Our first condition of motion is when acceleration is equal to 0. Acceleration is equal to 0 when there is no net force. So the net force equals 0. In other words, if there are any forces acting on the object, they are balanced by an equal and opposite force. So overall, the object does not feel a net force or experience a net force. In a situation such as this, the velocity is unchanging, meaning if it is 0 meters per second, it stays at 0 meters per second. If it is 50 meters per second, it stays at 50 meters per second. In which case, if I was going to draw this object, then for equal amounts of time, the object will cover equal amounts of distance. So if I had a camera which took pictures, say every second, then every second it took a picture, and I put all these pictures together, and I maybe took a picture of them alongside of a ruler, I would find that the distance between successive shots is always the same. So D1 equals D2 equals D3, etc. for equal amounts of time then. If I want to look at when the acceleration is not equal to 0, then I need to realize that the net force is no longer equal to 0. There is going to be acceleration if the net force is not equal to 0. That acceleration will be in the direction of that unbalanced force. In this case, the velocity will change, and in fact is changing constantly. If I was to draw a picture of acceleration, it would look different if the acceleration was greater than 0 than if it was less than 0. If the acceleration is greater than 0, what we find is that the distance is increasing. I'm just going to kind of eyeball this, but if I eyeball it correctly, I will agree with the way the diagram looks. Okay, it looks like it's accelerating almost in a uniform manner. And you can see here the distance between successive dots is increasing. Again, the time is the same between these pictures, but the distance is increasing. So if I call this D1, D2, D3, as I did in the first example, I will find that D1 is less than D2, is less than D3, and so on. We'll discuss the actual nature of the relationship between these distances at a later time. For now, all you need to know is that the distance is increasing. If acceleration was less than 0, then we would find just the opposite of this. It would start out covering more distance than it ended up covering. So here we can see that this object is slowing down. For equal intervals of time, it's covering less and less distance until which time it stops and it starts going in the opposite direction. Now in Physics 12, we examine these types of motions, constant acceleration and acceleration equal to 0 at the same time. The situation that we examine that deals with this combination is that of projectile motion. In projectile motion, we see an object which is horizontally experiencing no net force. So its motion horizontally remains the same. For example, if I was to take a picture of a football flying through the air, and all I did is look at the horizontal nature of that football, I would find that the distance traveled in equal intervals of time on the x-axis is equal. So let's just look at what that would look like if I was to draw that. Okay, I already know that, and then I'm just going to take this fact into consideration to make it easier to draw. I know that the flight of a football is parabolic. Now, that tells me that if I was to draw that motion of a football, it might look something like this. Not quite parabolic in this case, but we can imagine maybe. I'll just kind of curl this down a little bit more. Okay, so this football now flying at any point in time, from time 0 in this case, if I was to take pictures at equal intervals of time along its flight, I would find that the distance it covered was equal. So here's the football here, and then it's now notice from the y perspective, the velocity is changing. It starts off with a lot of velocity when it's just first thrown or kicked. You can see the distance it's covered from its initial point 0 to its first point. And then we have the next distance. And then we have the next distance. And again to the top. And you can see both motions that we've just described. On the x-axis, we see the constant motion, where a equals 0, and the spacing between those intervals is equal. On the y-axis, we see that the distance from one picture to the next is decreasing. That's due to the force of gravity. Gravity is pushing down on that ball and slowing it down in the upwards direction. But it has no effect on the horizontal motion because it's not acting in there. There's no net force acting in the x-plane. It's only in the y-plane. And since these two planes are orthogonal or perpendicular to each other, the force has no effect on the x, only on the y. So what we see in this case is we have two problems at once. We have an accelerating problem and we have a uniform motion problem with no acceleration. And we can see that this motion here will repeat itself on the way down for equal amounts of time. If the parabola is drawn properly, we will find that at those same intervals along the y-axis and the x-axis, the same pattern is mimicked. Now, in order to solve this problem, we will be required to deal with it one dimension at a time. In this dimension, we'll have a equals 0, and in this dimension, we'll have a not equal to 0. In which case, the kinematics equations here end up looking like this. All the other equations give us no information. This equation came from this relationship where a equals 0 Therefore, we're left with just this. The other two equations, this equation and this equation, which is just the square of this equation, simplified, making use of the first equation. Both of these have this term equal to 0 because it has an acceleration in it which is equal to 0, in which case we simply get the final velocity equals the initial velocity. The final velocity equals initial velocity. And that's what takes place in an accelerating plane where a equals 0. So these are more or less useless equations. In the vertical dimension, we have all these same equations, but this time a does not equal 0. So we can make use of all of them. And we do. In order to make use of these equations in either dimension, we need first to resolve the velocity that we're given into x and y components. In other words, resolve the velocity into the components of without acceleration, or the plane where there are no net forces acting, and the component in which the net force is not equal to 0. So I could pick any point on here, and a problem may give us any point on here, but if I just pick the initial point right here, let's say, where I've got my initial velocity, v0, I'm going to have an x component and a y component. And if I'm given what this angle is above the horizontal, then I can figure out what these two expressions are, and I can end up finding myself solving problems quite easily in either dimension, given that. And that leaves us until our next lesson.